Hello, my name is Lloyd Smith. This is a presentation of a paper entitled The Reverse Magnus Effect in Golf Balls that Ben Liu, Jeff Kensrud, and myself wrote for the Sports Engineering Journal. The work was performed at the Sports Science Laboratory at Washington State University. Before we talk about the reverse Magnus effect, let me present a few definitions for a ball traveling in air. It is helpful to use non-dimensional parameters. They can remove the effects of factors such as air density or ball size. We normalize speed using the Reynolds number, where for a golf ball traveling at 65 miles an hour, it is about 75,000 Reynolds number. The ball's speed slows due to a drag force that acts parallel and opposite to the direction of motion as shown here. It is normalized by a drag coefficient. If the ball has backspin, a lift force acts normal to the ball path, giving it extra distance. It is normalized by the lift coefficient, as was done for the drag force. It was first observed in 1852 by Heinrich Magnus, which is why we refer to lift as the Magnus effect. At low speeds, the aerodynamic flow lines around a ball are smooth, forming what is called a laminar boundary layer. The flow separates near the ball's equator, resulting in a relatively large wake with high drag and a drag coefficient close to half. At higher speeds, the laminar flow around the ball transitions to turbulent. The flow separates downstream from the ball's equator, where the separation points move closer together, reducing the wake size and lowering the drag. The significant reduction in drag at higher speeds is known as the drag crisis and is shown in this chart. The dimple patterns of a golf ball are carefully arranged to take advantage of this effect and give the ball its long carry distance. The drag crisis may also be responsible for the reverse Magnus effect. More on this later. When a ball traveling through air spins, the separation points move in the direction of spin. This example shows a ball with backspin, moving the separation points and the wake downward and producing a lift force, or the Magnus effect. Lift and drag forces are often measured from stationary balls in wind tunnels. This work takes advantage of modern speed sensors to get forces acting on the ball from its acceleration. The aerodynamics of a ball traveling through still air is not susceptible to error in the blockage correction factors or ball support fixturing needed with wind tunnels. To project the ball without scuffing its surface, a linear accelerator was used. The accelerator consisted of a pneumatic piston connected to a cradle. Speed was controlled by the air pressure used to accelerate the piston. The cradle contacted the ball with a high and low friction surface. At the end of the piston's stroke, the ball rolled out of the decelerating cradle, where a high friction surface on the top of the ball induced backspin. The spin magnitude was controlled by the length of the friction surface. The ball's speed and its vertical position were measured in a speed sensor, consisting of 3 light gates. Speed was found from the time and distance between the vertical light gates. The vertical position was found from the ball speed and the time between the first and second light gates, where a ball traveling in the high in the speed sensor would have a longer time than a ball traveling through the bottom of the sensor. In this experiment, ball speed and position were measured 3 times over its trajectory. Since the ball was traveling primarily in the horizontal plane, its horizontal deceleration and mass were used to find the drag force. Lift was found from the ball's vertical acceleration and ball mass. The vertical acceleration, in turn, was found from its vertical position and time, after subtracting the effect of gravity from its trajectory. We compare the lift and drag of 3 different golf ball models. They are identified as V1 for the Titleist Pro V1, CA for the Callaway Chromesoft, and BS for the Bridgestone B300-RX. While all of the balls are approved for regulation play, their dimple patterns differ. The V1 has rounded dimples, the CA has hexagonal dimples, and the BS has dimples with a flat interior. By comparing the response of golf balls with differing geometries, we can determine how universal the reverse Magnus effect is. Here we projected the golf balls through still air at a Reynolds number ranging from 50,000 to 200,000. The spin rate was constant at 2250 RPM. A characteristic drive crisis is apparent for all three models on the left. As expected, the lift coefficient is generally positive. All three models showed a reverse Magnus effect and a Reynolds number of 65,000. Showing the reverse Magnus effect is real, it affects multiple models, and it occurs at a relatively low speed. This means you can't blame your short drives on a reverse Magnus effect. Next, we projected the balls at varying speeds with a constant spin rate of 1750 RPM. The results are plotted as a function of the normalized spin factor, S, where when S is equal to 0, we describe no spin, and when S equals 1, the surface rotational speed matches the ball's linear speed. As seen on the left, the reverse Magnus effect is larger at lower speeds, but reduces again if the speed becomes too low, 50,000 Reynolds number in this case. The reverse Magnus effect tended to be larger at 65,000 Reynolds number for most of the models considered here, and this speed was used for comparison on the right, where all models show a reverse Magnus effect at roughly the same spin factor. We've shown the reverse Magnus effect is real and occurs for many golf ball models, but why does it exist? Consider a ball with a backspin traveling to the left at a speed roughly in the middle of the drag crisis. The top of the ball is spinning in the direction of the airflow, which reduces its local airspeed. This tends to make the flow on the top of the ball more laminar and moves the separation point forward. The bottom of the ball is spinning against the direction of airflow, which increases its local airspeed. This tends to add turbulence to the flow at the bottom of the ball and moves the separation point backward. The net effect is a rotation of the separation points counter to the spin direction, pointing the wake upward and producing a downward aerodynamic force or reverse Magnus effect. As an example, consider a ball traveling at a Reynolds number of 60,000 near the middle of the drag crisis and spinning at 1500 RPM. Spin causes the local speed at the bottom of the ball to increase to 69,000 Reynolds number, where the flow is primarily turbulent, while the same spin causes the local speed at the top of the ball to decrease to 51,000 Reynolds number, where the flow is primarily laminar. To illustrate the sensitivity of the reverse Magnus effect on the drag crisis, here we show the lift and drag of golf balls at 1700 RPM. While all three models again describe a drag crisis, the slope of CA is steeper than the others. On the right, we show the lift coefficient as a function of the slope of the drag crisis, where the slope is taken as a line through the local speeds at the top and bottom of the ball for each trajectory. Since the data here all have the same spin, the slope is equivalent to the difference in the drag, or turbulence, at the top and bottom surfaces of the ball. Notice CA, which had the steepest drag crisis, also has the largest reverse Magnus effect. We have shown that the reverse Magnus effect exists with three different golf ball models on different dimple geometries. We wondered if it occurs on other sports balls. Given our lab's history with baseball, we wanted to see if it had a reverse Magnus effect. The answer is not entirely obvious. Since the baseball surface has not been optimized as occurs with golf, its drag crisis is less steep by a factor of 8. A reverse Magnus effect was observed at a similar spin factor as we saw with golf. The speed of 84,000 Reynolds number is slightly higher than with golf, but is still on the lower end of speeds seen in play. Now to sum up, we've shown that the reverse Magnus effect is real and can occur with many types of sports balls. The reverse Magnus effect occurs over a relatively small range of spin and speed. The speed where the reverse Magnus effect is active is at the lower end of speeds observed in play. Thanks for watching, and we hope you enjoyed this presentation.